just as a quick review, let's go over scatter plots. You can see the definition of a scatter plot if you look at the PowerPoint. It says, is a graph used to display the relationship between two quantitative variables measured on the same entity. Data pairs, x and y, representing the two variables are plotted as a single point on a graph, with x, the explanatory variable, along the horizontal axis, and y, the response variable, along the vertical axis. All right. An inverse relationship, it says there is an inverse relationship between, when there is an inverse relationship between two variables, as one variable increases, the other variable decreases, and vice versa. So if we have a scatter plot, and we looked at several different, and in general, the data, as one increases, the other increases. So as you go to the right here on the horizontal axis, you go up on the vertical axis, then that is a positive relationship. Okay? And that's because if you were to, I mean, we're not doing regression lines yet, but if you think about like a line that's graphed through those, that would have a positive slope, right? So we say that that has a positive relationship. And if whenever we graph a scatter plot, if the points, like if for small values of x, we start out at large values of y, and then it goes down, then that would be a negative relationship. Okay, so I think I gave you a few examples the other day. There are several good examples. I was looking through the homework earlier, and one of those was something like the price of a gaming system and the number of units sold. So if there was some new gaming system that came out, let's say the PlayStation 5 came out, and they wanted $800 for it, there probably wouldn't be that many sold. There would be some, because some people would just save up money, you know, or have as much money as they need to buy it. But as the price goes down, let's say then a month later it goes down to $500. They have the cheap version come out. So there's probably going to be more people that are going to buy that cheaper version, right? So as the price goes down, the number of units sold would go up. So depending on, you know, which one of those variables we make x and y, we may have a positive or a negative relationship. Does that make sense? So if as one goes up, the other goes up, it's going to be positive. But as one goes up, if the other goes down, then that's going to give us a negative relationship. And then, you know, if we do our scatter plots and our points are everywhere, you know, we looked at like putting money into education and scores, and it said that actually if you increase teacher pay, studies have been done to show that it really doesn't increase student outcomes. So it takes a lot more than just throwing money at a problem like education. There's a lot of small parts that need to be fixed. So that would be no correlation. All right. And you can see these different scatter plots. They show a negative relationship, positive relationship, even no relationship on your PowerPoint. Okay. Now, not to scare you, but I want you to take a look at the formula for the correlation coefficient. It will be on the handout that I gave you, the PowerPoint. It's going to be on the back. of the first page. I think some of you can, if you're looking at it right now, you see why I said not to scare you. But I mean, it does have a lot of parts, okay? And so our goal is to understand the parts, understand how to figure out all of those values, and then how to calculate the correlation coefficient. And then we need to understand why we're doing it. Because we don't want to just do this stuff just to do it. All right? We need to understand why. Why is this value that we're figuring out, why is it so important? Okay? And we do use this through the rest of this chapter when we start talking about correlation and other values that are related to that correlation coefficient. All right, so we're not going to use that first formula there. We're going to use the computational formula. I mean, does the first formula work? Yes, it does. It works fine, but sometimes it's easier for students to understand the computational formula, how we would actually figure it out if we have to, we have to grind through that formula. All right, give me just 1 second. So you see an X there, you see a Y there, you see a lot of sigmas actually, a lot of sums that we're going to have to figure out. You see some square roots, you see some squares, and it's important that we keep all of that separate. So in my opinion, if you're doing this out by hand, we're going to need to make like a chart, kind of like with standard deviation or variance. You need to make a chart. That way you can keep all your values straight. Okay? So the computational formula, again, it's already written down for you, but I want to go through it, is R equals N times the sum of X sub I times Y sub I minus the sum of X sub I times the sum of Y sub I divided by the square root of N times the sum of X sub I squared minus the sum of X sub I squared. So this is N times the sum of X sub I squared, and this is, I guess I have one parenthesis a lot bigger than the other there. This is the sum of X sub I squared. So that kind of looks like, if you remember, that kind of looks like the formula that we have to use to find the standard deviation. I mean, somewhat, a little bit, okay? And then it's times the square root of N times the sum of Y sub I minus the sum of Y sub I, it's N times the sum of Y sub I squared minus the sum of Y sub I squared. So there's a lot of room for error here. A lot of room for error because there's so many little values. Okay, I found us an example to work through that's similar to a homework problem, and it was talking about eBay and the number of bids on an item and the amount that the item sold for. So what would you think? Let's just use common sense. And I mean, this, of course, won't always be true. But the more bids that an item has, more than likely, the more it's going to sell for. Now, I guess if somebody started something out at 1 cent and people were just like, bidding 1 cent, 2 cents, 3 cents, like that, then it would have a lot of bids and maybe it wouldn't sell for much. But in general, if you put an item on eBay, anybody here ever sold anything on eBay? Nobody? One person? I've sold a lot of stuff on eBay. I bet like every time that I upgrade my computer, I'll sell graphics cards, CPUs. Like my wife had a laptop that broke, and I just took it apart and sold the RAM, sold the CPU. So I mean, if you have broken components or you have components you're not using anymore, it's pretty easy to put it up on eBay. Somebody's going to need that somewhere, believe me. Or somebody's looking for something, like people that do repairs, they're looking for pieces like that. They're looking for broken cameras so that they can take it apart, use the parts to fix other people's stuff. So you may not make a lot of money, but you can sell stuff pretty. And they have other sites now. I always see the commercials for Let It Go. I've always wanted to use that, but I haven't. And then Craigslist, which I scary people on Craigslist, so I don't know if I would sell anything on Craigslist. Even though in bigger cities, a lot of people do that. I doubt the Craigslist listings for Wesson, Mississippi are very big. Maybe a surprise, though. All right, so here's the table that we're going to look at, and we're going to calculate this correlation coefficient R. So here is, and again, this is, we're figuring out correlation coefficient R on this set of data that is going to be the amount that an item sold for, or the price in dollars, depending on the number of bids. All right. So we have 114, 110, and 15, 120, and 18, 150, and 19, and 190, and 20. Now, there's going to be some problems that you work that's going to ask you to graph this. And so in your homework, it'll actually bring up a graph, and you can put points to make a scatter plot. Okay? But I'm not going to do that now, but it's pretty easy. It's just like graphing points on a, XY axis in the rectangular coordinate system. All right, so what all do we need? We need a lot of stuff, right? We need the sum of x, we need the sum of y, we need the sum of x times y, we need the sum of x squared, we need the sum of y squared. So that's all the sums we'll need, and then we'll plug them in our formula and we'll see what we get. Okay, so I'm going to make me a table. So let's make one column that is my x values. All right, so I'm going to say this is my top is my x value, and the bottom number is my y value. So x and y. So 100, 110, 120, 150, and 190. And if you're not, you need to be writing this down or pretending that you're writing this down. Alright, now I need to find the sum. And I am going to use a calculator, because that is the best way to do it. Alright, so I got the sum equals 670. Now I'm going to make another column for y. And I'm going to do the same thing. I'm going to try to keep everything as straight as possible. The neater I am, the more organized my table is, the easier it's going to be for me to find my answer, and the less chance that I'll make a mistake. Alright, so the sum of all my y values, I got 86. So we know we need the sum of x and we need the sum of y in our formula. We also need the sum of x times y. Alright, since I'm multiplying, it's going to be a little bit bigger number. Sum of those numbers. All right, and I got 11,860. I also need the sum of x squared.
To get the 11,000 number, you added like all the 14 numbers.
Yeah,
Okay.
let's take the sum. So I need the sum of x squared and the sum of y squared. So that means I'm going to have to find x squared and y squared. Alright, now I'm going to find the sum of those. I got the sum equal to 95,100. Now I'm going to do the sum of all of my y squared. So I've got to find y squared to do that. Alright, so I'll sum those up, and I got 15,006. 1,506. Okay, so I think that's all I need. I need one other value that was in my formula, and that was n. N is the pairs of data items that we have. Remember, I have an x and a y. So n is going to be equal to what? The pairs, so it's 5 pairs of items. N equals 5. All right, so I'm going to write the formula down one more time, just so we'll have something to go by. You can see it on your paper, of course. I wouldn't write it down. Unless you think you might need it. And I will never make you memorize these formulas. I will always let you use a formula sheet or give you a formula sheet. Alright, so we're going to plug our values into this formula. So remember, n is equal to 5 each time. So this is 5 times 11,860 minus, now we want the sum of x times the sum of y. So the sum of x is 670. The sum of y is 86. Divided by the square root of 5 times, no, the sum of x squared is this 95,100 minus the sum of x, which was 670. And then you have to square that times the square root of n again is 5 times the sum of my y. What's the sum of sum of my y squared? What's the sum of my y squared? 1,506 minus the sum of y squared. So the sum of y was 86. That's 86 squared. Alright, so what I would suggest doing is, I wouldn't try to punch all this in at once. I'd work out the numerator and figure out what that number is and write it down. So that's what I'm going to do first. So make sure that you understand how to punch this in your calculator and you get the same answer as I do. Alright, so when I worked out the numerator, I got 1,680. Anybody get that? Okay. Divided by, now what I would do is I would work out what was under the first radical and then work out what's under the second radical. Now we cannot get a negative number under the radical. So if something happens and you get a negative number under the radical, you messed up. Alright, so now what I would probably do is I would probably work out the denominator, and you're going to get a decimal, but I would carry that decimal out about 5 or 6 places whenever you work out the square root of 2660 times the square root of 134. Or 26,600. So square root of that times square root of 134. And I got this number, and again, carried out to a couple of decimal places because this is a formula, and the less decimal places we have when we use a formula, the bigger margin of error we're going to create. All right, so we want to round R to a couple of decimal places. So we need to carry it out to a couple more decimal places than we want to round it. All right, whenever I work that out, I got 0.8898. I'm going to stop, well, 48. And depending on what the problem tells me to round to, it's probably going to say to round to 2 or to round to 3 decimal places. If I rounded this to 3 decimal places, that would be pretty convenient, because that would make this 0.8. If I rounded to 3 decimal places, that's going to become a 0, and then that's going to become a 9. So that's the answer. Okay. Did you get the numerator and the denominator?
I got the numerator.
Probably not the denominator. Let's see. This was just 5 sets of data, or 5 data items. Can you imagine if there were 20 data items? Do you remember the scatter plots we were looking at last class meeting that had 20 or 30 data items? It can get very tedious to calculate this by hand. That is why there are lots of softwares out there that will do this for you. I hate to fumble around in Excel and not exactly show you how to do it. I started using Excel last year because I found I had too many students who, which is fine, they didn't have a calculator, which I'm not going to require you to buy this high dollar calculator. But if you are a college student here, you have access to Excel. All right, it comes with your tuition. So if you need to know how to get to it, I can show you where you can download it from. But you have access to that you can put on your computer and your aunt's computer, or whatever computer you're going to use. You can put it on there. Okay, as long as you're a student here. So what I'm going to do is I'm going to bring up Excel and I'm going to attempt to show you how to do the same thing. Okay. When I say attempt, it's because I haven't done it in a semester, and I might have to, mess around with it a little bit, but I believe I can remember how to do a scatter plot at least. And I think if I do the scatter plot, then I can figure out how to find R. All right. So what I'm going to do is I'm going to put the values from this table in 2 columns. All right. So again, that's what I'm going to do first, and then I'll show you. I'm just going to put them over here. All right, so here's what I've done. I just put the values in. All right, there's all kinds of tools over here. Like if I wanted to sum up a column, there's lots of functions here that you can use. You can even see there's one called standard deviation. So there's all kinds of functions that are built into Excel. One of those I know is a scatter plot, and so all I have to do is find the scatter plot option, and I'll be good to go. Let me see. Let me just look through real quick. Okay. Some data tools here. It's right around here somewhere. There's a table. It's right here. Here we go. Charts. I clicked on this recommended charts under insert. And I know somewhere there's a scatter plot. So you see right there, XY scatter. Alright, so what this has done is this has created an appropriate, and it did a Y and an X. It did my, yeah, it did it right. It did my X on the bottom, did my Y on the top. Alright. Now, there is a way, I believe, if I go to add chart element, and again, this, now once I put that in there, which was under insert, this is under design, I can go to trend line and linear, I believe is what it is, but more options sounds good too. I'm gonna see. So this kind of shows me a line that, and we're gonna calculate some values that will be associated with this line. So it shows me a lot of different, or it shows me that line that would go through this, but it really doesn't give me that much information. So let me see if I can figure out a little bit more. See, trend line, more trend line options. Here we go. And display equation on the chart. This is going to be related to something that we're going to do, that equation. So let me go back to that. I'm looking for the R value. This is display R squared value. Let's see. That really doesn't. See, it's a capital R. Let's just double check. Now that is what I got though. So, I was wondering if I could just show R, but there's R squared. It's kind of small there, so you might. If you were looking, well, yeah, you can see it pretty good. This right here is also, it's something that is very hard to calculate. Well, I'll say very hard. It's pretty hard to calculate, but it's something that Excel will do for you, and other graphing utilities will also do it for you. So where did I get all that from? I had to select the data items that I put here, and then I had to go to insert, and then go over here to charts. You can actually see there's a chart right there. And once you click on that chart, it's going to make this for you. And then if you go, once you do that, under design there's a add element or add chart element, and you go down to trend line. And more trend line options brings up all this stuff over here, where you can display the equation, the r squared value. So this capital R squared, if you take the square root of that, that's your lowercase r. But what, so this is just a way to kind of check your work. Maybe you have an online test and you can use this to help figure out those values. So, or if you have a calculator, if you have a TI calculator, you wouldn't believe how easy it is to figure out the values. A lot of the values that we're going to be learning how to find. Well, what does R actually mean? Because that's what's important, is why calculate this R value? Am I doing it just to torture you? You think that I enjoy? Some people struggle with number crunching like this. And this was, again, it's only 5 data items. If I put 10 data items down there and you get me to work it out by hand, I'm probably going to make a mistake. Unless I'm super, super careful. All right, but if it's 30 data items, I guarantee there's a very high chance I'm going to make a mistake. All right, that's why we use computer programs and software to do that. All right, but why would we want to figure out this value? That's the big question. Now this value of R, let's go back to your PowerPoint. There's some properties here that are listed, and this will hopefully explain kind of why we calculate R. The value of R is always going to be between -1 and 1. So R, the correlation coefficient, is always going to be between -1 and 1. And that's on your PowerPoint. If you have values that are close to 1 for R, or you have values that are close to -1, then that means that the data is tightly bundled around a line. Tightly bundled around a line. That just means that if we were to draw a line through the data, all of the points would be close to the line. They're tightly bundled. So let's look back at these points. You see our R was 0.890. That's kind of close to 1, but it is a little bit away. So if we go over here and we look at this line through the data, you can see they're kind of close to it, but they're not like all right on it. All right. And so the further you get away from -1 and the closer you get to 0, or the further you get away from 1 and the closer you get to 0, then the further all of the points will be away from the line. Okay? So that's one thing that the R will tell us. If we have a positive R, that tells us that we're going to have a positive relationship. It's going to, in general, the points are going to be going up. So we had a positive R. We had an R of 0.890. So you can see this is a positive relationship because the points are going up, and that corresponds to the R that we found. All right. If our R is negative, then it's going to be a negative relationship. So let me show you a few more examples. These are also in your PowerPoint on the next page. There are some other properties I'm going to read through, but just so we can understand, what R means. All right, so, and this is more points, so more than we had. You can see this R is 0.95. So what that means is, if I could draw a line through this data, then you can see they're tightly fit around this line. Okay? Notice that this is positive, and this is a positive relationship. Same here. This is kind of, this is even closer to 0 than ours, but ours was positive. You can see if I draw a straight line, the points are still around the line, but they're not as tightly grouped around the line. And the closer you get to 0, whether it's positive or negative, so if you think about those numbers on a number line, the closer that you get to 0 from either side, then the further spread apart those would be. I could draw a line like that, but you can see they're pretty far apart. I could draw a line like that, but you can see again they're pretty far apart away from that line. Okay? So I'm going to read through the properties. I'm reading straight off the PowerPoint, so you don't have to write all this down. Just read along with me. A positive association is indicated by R greater than 0 and an upward sloping relationship. Negative association is indicated by R less than 0 and a downward sloping relationship. A value of R near 0 means there is no linear relationship between X and Y. It does not matter whether you correlate Y with X or X with Y. You will still get the same value for R. If you look at all of those points, if you reverse the points is what it's saying, you're still going to get the same value. If you make your X's your Y's and your Y's your X's. If either variable is converted to different units, the value of R will not change. As a statistical measure, R is very sensitive to the presence of outliers. A single outlier can drastically affect the value of R. Because one outlier, think about it, is not only going to affect the sum of, say it was an outlier of X. It's not going to only affect the sum of X. It's going to affect the sum of X squared. It's going to affect the sum of X times Y. So one value that's an outlier will affect R. All right, some common, I guess your book says avoiding some correlation pitfalls. The saying that I was thinking about last class meeting was this, and it wouldn't have made as much sense then as it does today. Correlation does not imply causation. Because, like I told you, if I compared the amount of ice cream that was bought from an ice cream truck, and that was one of my variables, and then I compared that to a number of snake bites that was happening at that same time, yes, the amount of ice cream sold will probably increase as the number of snake bites increase, or vice versa. But it's not the snake bites that's causing people to eat more ice cream. It's the fact that the temperature is rising. The temperature makes snakes more active, and so then there would be more snake bites. So you can't make a correlation, or you can make a correlation between snake bites and ice cream, but snake bites don't make people eat more ice cream. I don't know, maybe they will when they're in the hospital. I don't know. But correlation does not imply causation. So if we do see some type of relationship there, that is called common response. For us to assume that correlation implies causation. In statistics, common response refers to the phenomenon where changes in both the explanatory and response variables, so that's the X and the Y, result from a change in a third variable. So like the temperature in our example will be the third variable. All right, the last slide there says a quadratic relationship is a mathematical relationship between two variables that follows the form of a quadratic equation of degree 2. The scatter plot of the data will look like a parabola. Everybody knows what a parabola looks like, right? No? That's your quadratic equation. That's what it's called. That's the shape. So I know everybody in here has graphed a quadratic equation at one time or another. But you can see this would basically be a U-shaped graph opening downward. So if you have, or a U-shaped graph opening upward, that is a quadratic relationship. All right. So we all know how to calculate R now. So imagine calculating R for these sets of data. That's a lot of values to figure out. A lot of stuff there. The more values you have, the harder it's going to be to calculate that by hand. So you might want to take advantage of any kind of technology that you can use. All right, moving on to the next section. Fitting a linear model. All right, so what do we know about linear? The word linear kind of reminds us of linear equations, which we've all learned about at one point or another. Okay, and we learned that our equation, y equals mx plus b, would give us that is the equation in slope-intercept form of a linear equation. Now let me ask you this. If I write this here, does that mean the same thing? The answer to that is yes. All right, when you add things, you can always change the order of them. The reason why I say that is because in statistics, we call it something different and we change the order. All right, why? That's just the way that it was done originally, and I really can't give you any better answer than that. It means the same thing mathematically, and we actually don't use the variables. We use different variables, but we do use this to help us figure out something about a set of data. All right. So the first example, I guess, that your book, or first thing your book starts talking about, is building a model that would help predict values in a scatter plot. All right, and the first example is talking about a test score, and for this test score, somebody claims to figure out that the test score is equal to 45 plus 3.8 times the number of hours of study time. All right, so according to this formula, supposedly this model. This is a mathematical model here. According to this model, I can calculate what I will make on the test by the number of hours that I would study. So if I didn't study at all, what does it look like I would make on the test? A 45, right? If I studied 0 hours, I would make a 45. What if I studied 10 hours? $45 plus 38, because 3.8 times 10 is 38. So if I study 10 hours, then according to this mathematical model, I would score an 83. All right. So here is a graph of this mathematical model. So it shows that hours of study time, see here at 0, and then here at 10 hours, it shows a prediction of what you would make on the test. Now, is that model exact? No. There's some error in that model, right? Just because I study 10 hours, I'm probably not going to make exactly an 83. All right. Now, could I say if I studied 10 hours, I would probably make a B? Maybe. I mean, some of these nursing tests you have to take, you'll be studying way more than 10 hours for if you're going to be successful. But there's some kind of margin of error there. It's going to be different for everybody. Right? So a better model here would be that the test score will be equal to 45 plus 3.8 times the hours of study time plus some margin of error. ERR. I just don't know what that error is. Okay? So I do know that if I studied for 10 hours, you know, if I study for 10 hours, then my score would be 45 plus 38 plus some margin of error. Or 83 plus some margin of error. And so that error could be positive, it could be negative, it could affect my score, you know, and it's going to probably be different from person to person. But let's say that the error was about 5 points. Well, that would be reasonable. So if I study for 10 hours, I'm going to make between a 78 and an 88. Okay. Of course, the larger the margin of error that I use, the higher range of values that I would get out. All right. And this linear relationship, again, that I'm using, we can think of it like we do a linear equation. Y equals mx plus b. All right. Where, of course, for linear equation, what is m? The slope. And what is b? The y-intercept. All right, so if we have a positive slope, then of course the line is going to go upward and we'd have a positive relationship. If we have a negative slope, then the line is going to go downward and we're going to have a negative relationship. So what am I talking about? Positive and negative, you know, on the scatter plots we were looking at, and some of these are on the PowerPoint. You know, and as x increases, y tends to increase. That's going to be a positive relationship. As x increases, y tends to decrease. That's going to be a negative relationship. So the slope of the line, if there was a line to go through that set of data, would be positive if there is a positive relationship and negative if there is a negative relationship. All right. So in the previous chapter, or not chapter, section, we were able to use R to help measure the degree of linear relationship that we have. What does that mean? It means, I told you the closer you are to 1, the more tightly fit all of the data items are going to be around the line, and it was going to be a positive relationship. The closer R is to -1, the more tightly fit the data items are going to be positioned around a linear line, and it's going to be a negative relationship. And so what we're doing right now, this is called regression analysis. So regression. And we're trying to use, what we're doing is we're trying to be able to predict values. We're trying to use x to help us predict y. And R is good, but R doesn't always do that. The correlation coefficient is not going to help us predict y if we have an x. To do that, we're going to need to be able to figure out an equation to help us predict a value. Okay? Now, traditionally in statistics, and this is where I'm going to show you the other variables. All right, so we had y equals mx plus b. We start learning about that in the 9th or 10th grade, maybe earlier. All right, in statistics, traditionally, we use y equals b sub o plus b sub 1 times x. And so I'm going to write the other equation right above it. Y equals, it was mx plus b, but if I change it around, that would be b plus mx. So you can see that b sub o, that's going to be our y-intercept, and b sub 1, that's going to be our slope. And it might be a good idea for you to write this down, if not on your PowerPoint somewhere, because we use this, and if you ever want to go back to the y equals mx plus b form so that your brain can understand it, you'll know how to arrange it.
And so that B sub O stuff, that's regression analysis?
What we're doing is regression analysis. This is going to give us an equation that we'll be able to use to come up with predictions about the data, and using this we'll be able to figure out a line that goes through the data. So, but this is all regression analysis, like all the stuff we're talking about right now. Yeah, talking about the relationships between the x and the y and trying to predict values. That's all regression analysis. This right here is an equation that we're going to use for our regression line, but we haven't really got there yet. So that's the y-intercept. Again, that's the slope. It's just written a little backwards. Now, if you use a TI calculator, you may see something like y equals ax plus b, or y equals b plus ax. I can't remember. But anyway, this function is in the calculator. All right, it's in, if you remember when we were looking at Excel earlier, this right here, this equation, even though it's in like y equals mx plus b form, and traditionally in statistics, that line right there, we would reverse those two values and we'd have y equals 8.7368 plus 0.0632x. So what is this value right here again? It's the y-intercept. Well, I don't see a y-intercept. Well, if I extended this line, that's going to touch right there at 8.7368. Alright, so just as a small refresher, I know that we all remember how to graph linear functions. The easiest way is like to make a table, right? You can always predict what y is going to equal. You probably hadn't thought about it like that, but you're figuring out what y equals when x equals something. What do they look like when we graph them? We all know what they look like, hopefully. This is just looking in the first quadrant, right? Just positive x's and positive y's. As you can see here, even though it's written backwards, it still means the same thing. The y-intercept here, right there. The slope, that means if I go up 2, I go over 1. Up 2, over 1. So on and so forth. Here, you can see the y-intercept is 8. You can see the slope is negative 2. So if I go down 2 and over 1, down 2 and over 1, you can see that's how we get that line. So again, if the slope is negative, the line would be going downward. The relationship is negative. If the slope is positive, then the line's going to be going up or upward, and the relationship is positive. The hard part is to figure out which line best fits the data. Because there's all kinds of lines. I could draw, if I had a bunch of points up here, if I had a scatter plot, let me show you. So I have this scatter plot. I could draw lines wherever I want to draw lines, you know. I could draw lines anywhere I want to. But which of these lines do you think better fits that set of data and could probably predict closer values here? B. Because it's a straight line that's going, it kind of goes through the middle of all these. Now, would it be exact? No, it would not. If I wanted to just plug in an x value, am I going to get this y value out? No, I would get this y value out. But it would be a lot closer than using this line and plugging in this x value and getting this y value out. Right? So B, this line, is the line that best fits the data. So you can see A and C definitely. Now C, yeah, C would work right here. C would work great right here. But what about over here? C's not going to work very great because that line's going to be way up here. Okay, so that's one of the things that we're going to work on, is we're going to figure out how to figure out that line, figure out how to find that line. All right, last thing for the day. We're running out of time. That line is called a regression line. Regression. All right, and there is a way for us to calculate B sub O, and there is a way for us to calculate B sub 1. And those ways, there are formulas that we're going to have to use. All right, there's also a way to calculate the error. Remember we talked about error? You know, they're not going to be exact. There's a way to calculate that. So that's what we're going to pick up next class meeting. So, you know, we have a scatter plot. Let's say it looks something like this. The regression line, again, it's not going to go through every point, you know, but it's going to be a line that best fits the data. Okay? And I told you that it's a linear line like our y equals mx plus b that we're used to from college algebra, but the formula is a little different. Instead of writing it like this, for the regression line, we write y equals b sub o plus b sub 1 times x. But it's basically the same thing. All right. And we had talked a little bit about error, I believe. Not a whole lot, but we talked a little bit about that, this line is not going to go through every point. It might go through 1 or 2 points, but there is an error, say from this point right here. There's an error because this is what we would predict that it would be that's on this line. So this purple point here, that's where we predict when x equals this, and y equals this, we predict it's going to be there, but it's actually not there. It's up here. Okay? So there is a margin of error there. And there's a margin of error between every point. Unless the line goes exactly through the point, every one of those little black dots up there, there's some little margin of error. Okay? And that margin of error is actually important. We want to calculate that margin of error once we can figure out the regression line. Or it has a couple of names. But once we figure out that line, it's important that we calculate that margin of error. Because it does have some meaning to us in statistics. All right. Let me show you an example. So I'm going to pull up a table real quick. Let me see if it is on your PowerPoint. Yes, it is. If you look, so we're on PowerPoint for section 5.2. If you look at the back page of, page 2, we're going to look at that chart there, that XY chart. So give me just 1 second while I pull this up so you can see it a little bit better, and I can see it a little bit better. All right. And of course, this is a pretty small data set we're looking at. Just like anything else that we do, the larger the data set, the more calculations are going to be. All right, whenever we start figuring out these lines. All right, so if we have this data set, again, that is in your PowerPoint. And let's say that we were to graph that data set on a scatter plot. Now, even though you don't know how to find the regression line, I am going to give you the equation of that, and then after I go over this example, I'm going to show you how to find the values of the line. So if we were to graph this, you can see it's in the next slide there. So this, I guess it's a light blue, bluish greenish line. This line, this is the regression line. And again, you don't know how to find that yet. Here's the equation. So here's b sub o right here, that first number, and there's b sub 1 right there. Okay, that's in front of x. And you can see it doesn't go exactly through any point, but it is the best fit of any line that we could possibly come up with. Okay, and you can see that it does predict what values that we get out. It just doesn't exactly predict the values that you get out whenever you plug in an x. For example, look, if I plug in a 2 right here into this equation, then my predicted value is whatever I get when I plug in a 2. So let's go through each value for x, or for each point. So this is the point 2, 3. The predicted value is what? So if I plug in a 2, it's going to be 1 plus 0.7 times 2. So that's 1 plus 1.4, or 2.4. Right, so the predicted value at this point when x equals 2 is 2.4. All right, but what is, and I can just put the x values here. I'll just put the x values. What is the observed value, though? What is actually there? Well, what is actually there when x equals 2? Y is actually equal to 3. All right. So you see how I can get a margin of error now? The margin of error, or the error that we're going to use, or that we're going to find, is always going to be the observed value minus the predicted value. So it's what it actually is minus what we get if we plug in a 2 into our regression line. So that would be 3 minus 2.4, or what? So I'm going to have to write a little smaller. 3 minus 2.4, or 0.6. All right, that's our error. It's not real. I keep saying margin of error, but that's our error. Just call it error. All right, now let's look at the next x value in our table. That was 4. So for 4, where does the predicted value come from? It's always going to come from the equation. So if I plug a 4 into my equation, then I'm going to have 1 plus, do I need to write that down? Do y'all? Okay. All right, so let me plug in a 2 right here. 1 plus 0.7 times 2. That was 2.4. Getting it from this equation right here. So if I plug in a 4, that's 1 plus 0.7 times 4. What the regression line does is it predicts the values that we could get. All right, it's the best fit line, but it predicts the values that we could get. So the prediction here is that when x equals 4, y is equal to 3.8. So the predicted value is 3.8. Well, what's the actual value? That's called the observed value. If you look at the point, you don't even have to have the table to find the observed value, or you don't have to have the graph. You can just look at the table. You know, this says when you plug in a 4, you get out a 2. Or if you look at the graph here, When you go to x equals 4, the actual value, the observed value, is 2. So to find the error, I wonder if I can make that a little bit bigger here. I'm going to write this smaller. Observed. So to find the error, we're going to say the observed value, which was 2, minus the predicted value, 3.8. So that's going to be negative, what? 1.8. Let me write that again. Okay, and I can do that for every value in my table. So if you look at your PowerPoint in the bottom right, that's what they're doing. That's what that table is. Bottom right table of your PowerPoint. They do that for every value. They do that for, here, let me see. If the homework asks you to find the error, this is how you find it. Yeah, well, there's a lot of other stuff that we can get from this, but if it asks you for the error, there's a certain name we can call the total error. All right, and I'm going to show you how to do that. So the other ones are, let's see, what are the other x values? So we got 5, 8, and 9. So 1 plus 0.7 times 5, take my word for it, that's going to be 4.5. And 1 plus 0.7 times 8, that's going to be 6.6. And 1 plus 0.7 times 9, that's going to be 7.3. All right, so those are all predicted. Those aren't actual values, but if we just had that line, we could predict what we would get out. You know, kind of like we went over, there was an equation that we had for hours studied and the grade you would make on the test. I mean, it wasn't exact, but it gave a prediction of what you would make on the test if you studied for 10 hours or something like that. Well, that's what we're doing here. We're looking at predictions. Now, what's the actual? The actual is called the observed value. Okay? So the observed value is the actual value you get from the table or you get from the scatter plot. So when x equals 5, y equals 6. When x equals 8, y equals 5. When x equals 9, y equals 8. And so the way that we find the error is we always say the observed minus the predicted. So this one would be 6 minus 4.5, or 1.5. All right, and then what? 5 minus 6.6, that's negative 1.6. And then 8 minus 7.3, that's 0.7. Now, if we sum all of those up, then that's the sum of the error. So if we add all those up, so we add up 0.6, negative 1.8, 1.5, negative 1.6, and 0.7. If you add all of those up, you get negative 0.6. And of course, we would want the smallest error possible. The smaller the error, the better the line fits. Okay? There's also another value called the square of the errors. It's called the sum of squared errors. The sum of squared errors. And it's just like what it sounds like. You take each error and you square it. So why would that be good? Because some of the errors you notice were positive and some of the errors were negative. So it's kind of like some of them canceled each other out. But if we square each error, then we're going to have a value that will be positive. And it's a better way of measuring the total error. Okay? So the sum of squared errors, you take each error and square it. I don't have enough room up here to make another column. I'm going to make it down here. All right? I'm going to name it error squared. That's what your book calls it. And I don't know how they just probably just put the square there without a parentheses. Now if you look at the table, it's kind of hard to see those little numbers. But if you look at the table, you can see what they did is they took the value and they squared it. They took each error and squared it. That means that everything you get out will be positive. Alright, so when I square the first one, for x equals 2, they got 0.36. For x equals 4, 3.24. For x equals 5, 2.25. For x equals 8, 2.56. And for x equals 9, 0.49. Again, why is that a good value for us to look at in the real world? That's a good value for us to look at because some of our error was positive and some of our error was negative. So if we just take the sum of our errors, then some of those negatives and positives are canceling out. So that doesn't give us a real good read or a real good feel to how good the line is actually fitting. But if we square all of those values, we make them all positive, and then we find the sum of all of that, that gives us a value that's a better representation of does this line fit or does it not fit that good. Okay? So if I take the sum of all of those values, the sum of the error squared, I get 8.90. Now, your book gives a formula for figuring it all out, and it's actually what we did, but the formula makes it look a lot harder than it actually is. I'll show you the formula just so you can see it and you'll know what it means, because it really wasn't that hard to find the error and then square it and take the sum of all that. But if you just need a formula to go by, here's the formula. And they call the sum of squared errors SSE. That's the sum of squared errors. So remember what this was. What was this? You remember? That would be the observed value first. So that's the observed. And in my mind, I think about that like that's the actual. And then this right here, that is the predicted value. And that comes from the equation of the line. The regression line, or it has another good name too. All right. And so right here it just tells you, hey, this is what you're doing. It's just another way to write it. Again, it looks a lot more complicated when you start looking at the formulas. But if you look at the example, it's not too bad. All right. So if you were to find the sum of squared errors for multiple lines going through a set of data, whichever one had the smaller, whichever sum of square errors is smaller, that's the best line. The smallest of all lines. So if we figure out a line, if I show you an equation, how to figure out this great line that's going to go through the data, it's guaranteed that that line will have the smallest sum of squared errors. All right. I know it doesn't sound like a big deal, but I mean it is if we're trying to predict values. If we're trying to make predictions into the future using a set of data, the line that we use to represent the set of data to predict values needs to be the best line that is the closest to all the points. Okay? And so that would be the line that has the smallest sum of square errors. Another name for that line, that best line, the best line, is called the least squares line. So that's another name for it. Because it has the smallest sum of square errors. Sum of squared errors. Now, why can't we just use the errors? Because again, the errors, some of them are positive and some of them are negative. And if you add them all together, the negatives and positives cancel everything out, cancel stuff out. Okay? So it's important to have a value. If we're going to start comparing different lines, it will be important to have a value that has the smallest, it will be important to have a value that doesn't consider positive and negative values, just considers positive values. All right? And so to do that, we simply square each value. All right, now, has anybody ever heard of, probably not unless you've studied mathematicians or had really good algebra in high school, Carl Gauss, Gauss. He actually come up with a formula to figure out this least squares line. All right, one time you may have heard of him. There's something in algebra when you start going over matrices called Gaussian elimination. So you may have heard of him then. You may have actually done some of his math and never known that you were doing his math. But several hundred years ago, he come up with the equations to find the slope and y-intercept, the m and the b, or in our equations, the b sub o and the b sub 1. Okay? And so they look a little daunting. They look a little complex. I mean, it's not real easy to figure out these formulas, so they had to be kind of complex. If you look at the bottom of page 3 of your PowerPoint, you'll see the two formulas for the slope and y-intercept of the least square line. Notice that you need b sub 1 to find b sub o. So I'll put the box up here just so you can see it, but it is on the PowerPoint. So if we have a small set of data, we could use these to help us figure out that least squared line to find the b sub o and b sub 1. Know that there are ways in calculators or in Excel to figure this stuff out. I mean, we all know what an x is. We all know what a y is. So this is x times y, the sum of x times y. We've done that. You know, here's the sum of x, here's the sum of y. Just know that's the product of those two. You know, this is the sum of x squared, so you'd have to have an x squared column, and then take the sum of all that. And this is the sum of x squared. All right, so it's not too bad, even though it looks kind of bad. It's just a lot of number crunching, a lot of calculations. Now, again, in Excel, I showed you how to do a little bit. So let me put the values from that table in Excel and remind you how to use Excel to find our B sub O and our B sub 1. Okay. I'm just going to need these values. So I'm going to type these values in Excel, and then I'll bring it over and show it to you. 2, 4, 5, 8, 9. Okay. So I typed those values in Excel. All right, and then I'm going to select those values, and I'm going to put them in a scatter plot. So if you go to Insert, you look at these recommended charts. You can see that one right there is a scatter plot. Let's do a scatter plot. All right, so there it is. Now, if I want to display the least squared line, I have to add an element to the chart. I have to go here, go down the trend line, and I'm going to put in, I think I can just go straight to more trend line options. Let's see. It may or may not let, okay, so put in the linear. See, that's the line. I want to see the equation. Okay. So it looks like what we were working with, and let me see if I can change the font here to make it bigger. You know, you saw what the equation was in the book that it used. You know, of course, things were rounded. Let's see, font. Come on. A little bit bigger. So in the book, we were using what? The first that equation we wrote down, it was y equals 1 plus 0.7x. So they were using rounded values. Okay, that's 1 plus 0.7x. If you round the y-intercept to 1 and you round the slope to 0.7. All right, and of course we would have to look at the directions to see what to round those to. So which one of these is my B sub O and which one of these is my B sub 1? So this one right here, that's my B sub O, the 1 point whatever. And then my B sub 1 is right here. It's the slope. Just know that it's generally written the other way, like this comes before that. So it's not hard to find the value using Excel. Has anybody tried this in their cell phone? Not in a cell phone?
I tried to do it like in Excel with my phone.
Mm-hmm.
And it didn't have the option to, like it had the design, chart design, but it wasn't option to put the line or whatever. You couldn't have it. So you couldn't figure it out. I ended up figuring out how to do it on calculator, but
Okay. I guess I would have to see how it looks on your computer. You know, did you select the data? Did it just didn't have this? Or?
it had that, you could do a scatter
Okay.
plot or whatever, and it pulled up the scatter plot, but it didn't have a way to like, see how yours says design and format?
Yeah.
It didn't have the design button, so you couldn't like find
Okay.
you couldn't add a chart element and insert the.
So there has to be some way to turn this tab on. I just don't know how. If it's not showing. So did you use a laptop or a desktop or? Okay. So Yeah, if you're having that issue, let me know, and I'll try to figure out your problems. But it's under trend line options. That's where you're going to get to where you can go down and change that. But so maybe if you go to the help and you just search for trend line option or trend lines, it might help. I don't know. But I know for me to get to it, I got to go to trend line options and then scroll down and click display equation on chart. Okay, did it again. You can also display the R squared value. So that's something that we're about to go over. All right. So there's another example in the book. I'm going to throw it up here. We're going to look through it real quick just to try to help solidify these definitions and hopefully help our understanding of what we're actually doing. So something that most of you probably haven't had to do yet, because you probably had somebody do it for you. Some of you may have already done this, but has anybody in here ever bought a vehicle? Probably not. Maybe. You know, when you buy a vehicle, as soon as you drive it off the lot, there's a huge loss in the value of the vehicle. That's very sad, but it is. And then as your vehicle ages, what happens? The value of your vehicle goes down. So, here is a chart that lists the age of this Honda Civic LX sedan, the asking price. So it's a table that has two columns here. So it's just, here's the age and here's the asking price. So of course we have, you know, multiple people selling this vehicle. That's how old it is. And so all the way down to 6 years old. Okay. So if we did calculate the slope and y-intercept with this data, here's what we would get. And you don't have to use Excel to do it. You can crunch the numbers. I know some people are like, shoot, I'm not doing that. Well, with a small data set, you can do it. You can crunch the numbers pretty easy. But if it's a large data set, this would take a little bit longer. But if you did crunch the numbers, you could figure out that your B sub O, or the y-intercept, is this number, and your B sub 1 is this number. Now, this is going to be what? Y equals, what do I write first? B sub O. So $19,198.32 plus, or actually it's going to be minus because that's a negative slope, minus, which makes sense because each year that you subtract, you know, if X is the number of years, each year that should make the price go down more. All right. Now this gives us predictions. This doesn't give us actual values. If I plug a 6 into this, I'm not going to get one of those numbers from the table. The numbers from the table are the observed values. The numbers that we get out of the formula, those are the predicted values. Yes?
So, in order to get those numbers like the BC code of 19,000 number, you would use the formula that you decided to do?
Yes. You would use these formulas or type it in your calculator or use Excel. But using these formulas with that many data values is going to take a little while. All right. So if I type these into Excel, these two data sets, The age of years, that would be my X values. And the asking price, that would be my Y values. All right, and I got it to graph it and come up with an equation, which we just came up with the equation. It would probably list the X value first, just like this figure I'm about to put up here. All right, it wouldn't look this pretty, but it would look something like that. And it would give us the equation. This is the scatter plot. So it looks like that line is pretty closely fit there. Well, what all could I get from that line? I could figure out the error. I could figure out the sum of squared error. Let me show you the table. I'm going to show you another table. This is a table where all that's been done. And more than likely, if you were doing a homework problem, even if you get the equation, if it asks you for the sum of square error, that equation doesn't give you that. Okay, you need the equation to figure all that out. So here's the table. So you use the technology to get the equation. This equation right here. And we have all of the observed values here. That's the Y values. To find the predicted values, we have to plug in this number into our equation. So we have to plug a 1 in to get the predicted value. You see? You plug a 1 in the equation right there, you get this. That's why it's the same thing here and here. Because if you plug a 1 in, you get the same answer. You plug a 2 into the equation, you get the same answer for all three of those. And you plug all those numbers in, that's what the equations give you. Then to get the error, what do? You say the observed price minus the predicted, or the predicted minus the observed? Observed minus the predicted. So then you can see, here's all the errors. Then you can see, here's all the errors squared. And if the problem said, what is the sum of squared errors, and you had to figure that out, there it is right there, the sum of squared errors. It's a really big number. But this is the best, or it's the regression line, but it's the least squared line. All right. Is there any questions?
Is there any way to add those numbers up in Excel, or those are the ones you just have to do in the calculator?
There is a way to add them up but you have to type these in. And there might be a way to actually there may be a function to call that. I just have never done that with Excel. But I know if you type them all in, you can just select them and then hit sum. So you can go, like, I know these aren't the numbers, but let's say these were the numbers. If you select a column, so let's say I selected those. There's a button over here for auto sum. You can take the sum of the numbers and it'll put it right there. So if you do type all those values in, then you can just select them and hit sum and it'll do it for you. Like a little built-in calculator. So that finishes 5.2. 5.2 generally gives students some issues because, I mean, what do we have to do? We have to be able to find those two values, the b sub o and the b sub 1. And then we have to be able to find the error and the sum of squared errors. And sometimes that takes a little while. Now, doesn't mean that there aren't easier ways to do that. Technology will actually, there are some programs that can spit all this stuff out for you. But I'm not going to require you to use those formulas. Just know you can do this out by hand, even though I wouldn't suggest it unless you have to.